Hello and welcome. Today, we're diving into the fascinating world of bio-inspired robotics. Think about it. Nature, through millions of years, has perfected designs that are incredibly efficient, tough, and adaptable. What if we could learn from those designs to build better robots? That's the core idea here. It's more than just copying. It's about understanding the principles that make living things work so well and applying them to engineering. So, why look to nature? Biological systems are masters at solving complex problems. Animals navigate tricky terrain, adapt on the fly, and perform delicate tasks with amazing agility and very little energy. These are exactly the kinds of abilities we want in robots, especially if they need to work in unpredictable environments or alongside humans safely and effectively. By studying nature's experts, we aim to create robots that are more versatile, resilient, and adaptive. Let's look at some exciting examples. One huge area is movement or locomotion. We have legged robots inspired by cheetahs for speed, or cockroach-like robots like RX that can scuttle over rough ground reliably. Robots like StickyBot mimic geckos to climb smooth walls, using special adhesives. There are even robots inspired by kangaroos, aiming for energy-efficient hopping. And it's not just land. Tiny drones like RoboBee copy the wing motion of bees for hovering, potentially useful for pollination or surveillance in tight spots. Larger drones mimic birds for quiet flight. Underwater, fish-inspired robots use efficient fin and tail movements for exploration. Snake-like robots can slither into collapsed buildings for search and rescue, while mole-inspired bots aim to burrow effectively. Some new robots, like the M4 Morphobot, even combine multiple modes: rolling, flying, walking, just like some versatile creatures in nature. Beyond movement, we're borrowing from nature's senses. Think vision systems based on insect compound eyes for a wider view, bat-like echolocation for navigation, or artificial whiskers for sensing in the dark. Manipulation is another key area. Soft robotics, often taking cues from octopuses, is booming. Imagine flexible robotic arms that can change stiffness to gently grasp objects, perfect for delicate tasks or even minimally invasive surgery. These soft robots, made from flexible materials, are inherently safer around people and can squeeze into places rigid robots can't. Finally, there's swarm robotics, inspired by ants or bees. Instead of one complex robot, you have many simple ones working together on tasks like exploration or environmental monitoring. What's next? Advances in materials science are crucial. Think artificial muscles, self-healing materials, and structures that can change stiffness. Artificial intelligence is also key, helping robots learn and adapt more like living organisms. The big goal is greater autonomy, freeing robots from tethers and constant human control. The potential applications are vast: search and rescue, environmental monitoring, medicine, from surgery to rehabilitation, logistics, exploring other planets or the deep sea, agriculture, and even security. Of course, it's not easy. Replicating the sheer complexity and energy efficiency of biological systems is a huge challenge. Powering small, autonomous robots for long periods remains a major hurdle. And creating truly intelligent, adaptive control systems still requires breakthroughs. But bio-inspired robotics is constantly pushing boundaries. By learning from nature's ingenuity, engineers are creating robots that are more capable and adaptable than ever before, poised to make a real impact across many fields. It truly shows that sometimes the best solutions have been evolving right under our noses for millions of years. Thanks for tuning in.